Welcome to the Masters in Telecommunications program of the University of Maryland at College Park. My name is Alejandra Mercado, and I am Associate Director for the program. Well, today we're going to talk about neural networks backpropagation, and it is our follow-up lecture on our subject of neural networks. So let's get started. Let's zoom out and remind ourselves about neural networks. We can have an input layer, and these are the layers of features that we input into our estimation. In this example, we have two hidden layers, and each node is interconnected with edges that will have their own weights, and then the last hidden edge is connected to the output layer, which outputs the estimate for our neural network. So for example, if you input as features a mouth or beak, and a feather or fur, and a paw or talon, then after the neural network has used these features and propagated through, it should be able to give you an estimate. Is this picture of a bird, or of a dog, or of a fish? So far, what have we seen in past lectures? We talked about regression estimation, and we used the steepest descent algorithm to train our parameters for regression. Then we talked about neural networks. What advantages do neural networks have with respect to regression? When do we want to use neural networks? And we also talked about the activation function. You could either use the sine function or the signum function. And why did we choose to use the signum function? Today we're going to talk about training, how to train our neural network. We're going to talk about forward propagation and back propagation. And just to give you a taste, after this lecture, we're going to talk about regularization and what's our best practices for random initiation, because they're not the same as for regression, like linear regression. Let's look at an example of a very simple neural network. In this particular case, we have three features as inputs, one hidden layer with two nodes, and one output. So we have three features that we input, plus a bias term, one hidden layer, and the edges connecting the input features to each of the two nodes of the hidden layer each have their own weights, W12, W13, etc. And each hidden node has an output, so we have two outputs for the layer 1 hidden nodes. And these outputs are connected to the output node. We have only one of them, and each one of these edges have their own weights as well. And in this particular case, we have one output, Z1. Remember that both the input layer and each hidden layer must have a bias term, which we default to the value of 1. So x0 is equal to 1 and y0 is equal to 1. In general, we could have D input features, NH nodes for the hidden layer, and C output nodes. But in our case, D is equal to 3, NH is equal to 2, and C is equal to 1. All right, let's talk about feed forward. What happens at one of these nodes? The output of this hidden node here is going to be equal to the sigmoid function applied to the weighted addition of each one of the inputs. So you have input 0 times W20, x input 1 times W21, input 2 times W22, and input 3 times W23, which is over here. Then you apply, once you've made this weighted sum, you applied the sigmoid function. We give this weighted sum a name. We call it net sub 2, and we call it sub 2 because this is the output of node sub 2. And if you notice, this weighted sum looks like a dot product or an inner product of two vectors, a row vector of w's with a column vector of x's. And later on, we're going to be using the vector format for this a great deal. So we write it right away as the row vector of weights times the column vector of inputs. All right, let's now look at the output node. The output node similarly is going to be we take the weighted sum, each one of the hidden node outputs, y0, y1, y2, y0 is the bias term, so that's just equal to 1. And each one of them is multiplied by their corresponding weights. We give them a capital W as opposed to the lowercase w we used for the hidden nodes because it'll just be easier to keep track of it. Later on, we're going to dispense with that distinction. This weighted sum, which is a scalar, again, we're going to call it net 1. And the 1 is because we have a single index for our output. And it can also be written as this scalar is a product of a row vector with a column vector. The column vector are the y0, y1, y2, and the row vector are these weights, w10, w11, w12. All right, let's keep going. Remember now that the bias terms are always going to be 1. If we had another hidden layer, their bias term would also be 1. The output, therefore, is the sigmoid function, this sigmoid function of this product of a row vector of w's times a column vector, 1, y1, y2. But we also know that y1 and y2 can be obtained from the inputs. And how do we do that? Well, we know that y1 is equal to the sigmoid function of the weighted sum of all these weights times the input vector. And there it is, the sigmoid function of the input vector, column vector, times the row vector of these weights. And y2 is equal to the sigmoid function, this sigmoid function, of y2, this row vector, times x, this column vector. And our neural net will perform well or poorly depending on our choices of the capital W's and these lowercase w's. So the purpose of training is to figure out, with the data that we're given, what are the best choices for these weights that are applied to the edges. Let's say that we have one training point, and I know you're going to think that seems like a very bad idea to just have one training point, but you'll see later that with all the sub-indexes that we have to keep track of, having just one training point will help us to understand what's going on. So we have the one training point of some x's that you input here, and it should produce this output. We know ahead of time that that is the desired output for this input. We want our neural network to produce this output to be as close to this intended output as possible. So therefore, we define our training error, or if you prefer, you can call it a cost function, to be the distance between the desired output and the output that we actually get. That distance is squared, and we add them over all the possible outputs. In this particular case, we only have the one output. So in this particular case, C is equal to K, which is equal to 1. And we only get a single term, 1/2 T1 minus Z1 quantity squared. We use the gradient descent to select our best parameters, and we've talked about this in previous lectures. We know that in this case we're not using an equal sign. This is an assignation. It means we replace WPQ with the old WPQ minus eta, the learning rate, times the partial derivative of our cost function from the previous slide with respect to WPQ. Now, in this particular case, I put lowercase w, but in reality, either lowercase or uppercase, it doesn't matter. This update formula works the same way. All right, but let's start finding out what is this update going to look like for the capital W's, the ones that feed into the output node. We know that in our particular case, we only have the one output, so we need to find the partial derivatives for 3 cases. The partial derivative of the cost with respect to W10, this guy here, with respect to 11, this guy here, and with respect to 12, this guy here, so we can update each one of them iteratively until they converge to good and proper, well-working values. We need that partial derivative. And in order to get that partial derivative, we use the chain rule of derivatives. In other words, we take one partial derivative that is not really obvious how to solve it, and we replace it with two partial derivatives that each individually are easier to solve. And you're going to see why these are easier to solve. So this is the partial derivative of W10 can be replaced with partial derivative of the cost with respect to net 1 and times the partial derivative of net 1 with respect to W10. And we do the same for all three of these partial derivatives. Now, at this point, I want to define, or we define, the sensitivity of output unit K. And the sensitivity of output unit K is equal to the partial derivative of the cost with respect to net sub K. And we put a minus sign in front of it. And you're going to see later how this is useful, but for now, just sort of accept that we're going to replace these three terms with deltas. There they go. We're going to replace those partial derivatives with the sensitivity for the output, and we're left trying to figure out, well, what is this? And also, what is this for each of the cases? Let's remind ourselves, what is net 1? Well, net 1 was equal to the weighted sum, the argument of the sigmoid function. So we're going to tackle one at a time. The derivative of net 1 with respect to W10 is equal to what? It's the derivative of this weighted sum with respect to W10. But W10 is not here, and it's not there either. There's only one term in here that has W10. That's the first term that's multiplied by 1. This partial derivative, therefore, is equal to 1 from here plus 0 from there plus 0 from there. Let's look at the second one. The partial derivative of net 1 with respect to W11, again, this is a linear function. This guy doesn't have 1, 1, so this is going to be 0. This one does have W11, so it's going to be whatever's multiplying W11. There it is. And this guy doesn't have W11, so it's going to be 0 as well. So we get 0 plus Y1 plus 0. And the last of the three is going to be the partial derivative of the weighted sum with respect to W12. Again, this term is going to be 0, this term is going to be 0, and this term is going to be whatever multiplies W12, which happens to be Y2. So we have these three partial derivatives, 1, Y1, Y2. They happen to actually be exactly the output of the hidden nodes, the nodes from the hidden layer. In general, when you take the partial derivative of the argument of the sigmoid function, you're going to get whatever output of the previous hidden node you're corresponding to that weight. So it's always going to be a bunch of zeros and then one output of the corresponding hidden node. Let's keep going. Let's tackle the output sensitivity. What is that thing? Well, the output sensitivity, we defined it to be -1 times the partial derivative of the cost with respect to net 1. So let's put in the formula for the cost. Now, in general, the cost had a summation from k equal 1 to c, but in our case, there's only the one term, so that simplifies a lot for us. We get the partial derivative of 1/2 times the desired point, that's what we're targeting, and this is what our neural net actually produces, the error between those two, the distance between those two squared. Again, this is not too trivial, so I'm going to use the chain rule again. We replace a slightly more difficult partial derivative with two easier partial derivatives. You take the partial derivative of the cost with respect to Z1 times the partial derivative of Z1 with respect to net 1, and that's using the chain rule. Now, the partial derivative of this first term is going to be, well, 1/2 times 2 times the parentheses term, so it's there's a minus sign there, so it's minus 1/2 times 2 times the parentheses term, times the derivative of what's inside of the parentheses, which is -1. So there's the -1. And we have the other term, derivative of Z1 with respect to net 1. Let's keep going. The -1 and the -1 cancel out, and the 2 and the 2 cancel out. So we end up with a simplified version, which is T1 minus Z1 times the derivative of z1 with respect to net1. Now that derivative here, it depends on the sigmoid function. Why? Because z1 is equal to g, the sigmoid function, applied to net1. So you're taking the partial derivative of g with respect to its argument. We can just call that g prime. In general, the delta function, the sensitivity, output sensitivity for node k of the output is going to be the distance between the desired output, the one that we're targeting from our training data, and the one that our neural net actually produces, times g prime applied to net k. So now we're going to get the derivative of the sigmoid function, which we need for our previous calculation. Now, the derivative of the sigmoid function is basically we're taking the whatever argument it has and taking the derivative of the sigmoid function with respect to that argument. And we chose 1 over 1 plus e to the minus x, our sigmoid function, as the activation function. I like to take the derivative basically expressing it as a power because it just comes out easier. Anything to a power of minus 1 is equal to, when you take the derivative, is equal to minus 1 times that thing to the power of minus 2. And then on top of that, you have to multiply it by the derivative of whatever the internal arguments are. In this case, because of linearity, we have the derivative of 1 plus the derivative of e to the minus x. So that's going to be 0 plus minus 1 times e to the minus x. So now we have that the derivative of the sigmoid function is equal to 1 plus e to the minus 2 times e to the minus x. And that is the derivative of our sigmoid function. Now, it's interesting that we can rewrite this in a very convenient way. Essentially, the squared of the denominator can help us to rewrite this product as 1 over 1 plus e to the minus net 1 times the numerator divided by the other 1 plus e to the minus net 1. Now you might think, what's the point of that? Well, if you notice, this term here happens to be g of net 1. It's just a plain old sigmoid function. And that's pretty neat. We can take it one step further. If we add and subtract 1 to the numerator of this term, then we can rewrite that as 1 minus the sigmoid function again. So it turns out that the derivative of the sigmoid function is equal to the sigmoid function times 1 minus the sigmoid function. All right, so now that we have the derivative of the sigmoid function, let's plug in our findings. We're still on the capital W's, and we want to learn how to update the values in an iterative fashion so as to train our W's with 1 point of training. We know that the partial derivative of the cost function with respect to W1J can be, we use the chain function to break it into two smaller and easier partial derivatives. And we know that the first of those two we define to be minus the sensitivity of output node K. We only have one output node, but that's fine. And we already figured out what this other partial derivative was going to be. So the sensitivity was equal to the distance between our target point and the point that our neural net produces times g prime of net 1. We just talked about what that was. And we also figured out that the last partial derivative was simply whatever output of the hidden node was multiplying that particular weight that we're interested in. And we just replaced g prime with g times 1 minus g, which we just derived a minute ago in a slide. So this is the update rule for W1J, like for 1, 0, 1, 1, and 1, 2. This is how we update each one of those weights. In general, if you have more than one output, you apply exactly the same rule for each one of the output nodes. And we know that each of the output nodes is going to have an output sensitivity, and we can plug that into our steepest descent update method. Okay, so we're done with the output nodes here. Later on, we're going to rewrite this in a more formalized way in vector form so that it's much easier to program. Okay, let's tackle the lowercase w's. And we have a lot of them. We have from all of the input nodes to each of the 2 hidden nodes, we have to figure out how to update and train each one of these little w's. Again, we're going to focus on one of the hidden nodes because otherwise it gets kind of cluttered and messy. Let's look at how we would update each one of these little w's that are weighting the inputs into this first node. Again, the steepest descent tells you that that's going to have the learning rate times the partial derivative of the cost with respect to whichever weight we want to update. Here we're going to sort of use the chain rule on steroids because it gets long. Each one of these, instead of using the chain rule once, we're going to use it twice. So we're going to replace each partial derivative, which is not too easy to do, with a partial derivative that's much, much simpler. The derivative with this cost with respect to y1, the derivative of y1 with respect to net 1, which is inside of this g, and the derivative of respect to net 1 with respect to weight 10. And this is going to be true for each one of these weights, and actually it's going to be the same for both hidden nodes. Let's keep going. Let's look at one of them in particular. What is this going to look like? Well, this partial derivative is, here's our cost function on the top of the derivative, and here's y1 in the bottom of the derivative. We're going to have to use the chain rule again, and we replace it with 2 easier partial derivatives. We insert the variable z1 because it's just easier to deal with these. When you take the partial derivative of the cost with respect to z1, it's much easier. It's just 1/2 times 2 times whatever's in the parentheses times the derivative of whatever's in the parentheses times the derivative of z1 with respect to net 1 times the derivative of net 1 with respect to y1. Now we know that z1 is equal to g of net 1. So g of net 1, when we take the derivative with respect to net 1, that's just g prime. We already saw that before. We're following the same kind of step, and that's a good thing, so we don't have to reinvent the wheel. This other guy is going to be the derivative of the weighted sum with respect to a particular hidden node output. Again, this is a linear combination of stuff. So taking the derivative with respect to one of them is just going to be whatever weight is multiplying that guy. So in this particular case, it's going to be W11, and it's always going to be like that, and that's a good thing. So now we have the partial derivative of the cost with respect to y1. We have an expression for it. And in general, if we had C outputs, then instead of having T1 minus Z1 times G prime of net 1, you would have this summation. But I'm just writing this down so when you see it on the textbook, it won't confuse you, like, where did she put that summation? Well, there it is. It's just that in our case, we only have one output. And for our sigmoid function, we know that G prime is equal to the sigmoid function times 1 minus the sigmoid function. In other words, G prime is equal to G times 1 minus G. We can plug that in right now. And this derivative of y1 with respect to net 1, well, what is y1? It's equal to the sigmoid function of net 1. So that is a very simple sigmoid function. It's the derivative of the sigmoid function, which we already know for our sigmoid function is G times 1 minus G. There we go. And this last one is the partial derivative of the weighted sum with respect to the weight that we're looking at, the weight of interest in this case. And this is a linear combination, so that's just going to be whatever is multiplying this weight, which happens to be, in this example, the thing that's multiplying W10 is X0. So there is our partial derivative of the cost with respect to W10. So now let's look at the big picture again. We know that for each one of these little w's, we have to use the partial derivative of the cost with respect to each of the little w's, and we use the chain rule of derivatives in order to simplify that partial derivative, and we figured out what each one of those segments were. So we can go ahead and write it in, replace it for our partial derivative, and let's talk further about what this is. We already defined that this particular term here was this output sensitivity delta sub k, for the output sub k. So we could rewrite this as the summation of delta sub k times wkj, and everything else stays the same. What we're going to do now is define the sensitivity of hidden node k right here. This hidden node k has a sensitivity. We're going to define it as the derivative of the sigmoid function times exactly this summation here. In other words, this term g prime here is there, and this, we can write it as an inner product. We can write this vector of weights times the vector of delta functions and write it, this scalar is the inner product between this row vector and this column vector. We just defined this entire segment here to be called the sensitivity of hidden node j, so we can replace it as the partial derivative of the cost with respect to wji is equal to minus the sensitivity of hidden node j times the input I. We're good. So we have our gradient descent for output nodes as well as for hidden nodes. Either one of these is going to follow the same gradient descent method that we learned before, and we found out how to get those partial derivatives. For the output nodes, the update rule is going to be that you replace any wkj with wkj plus the learning rate times the output sensitivity times the associated output of the hidden node that has j in it. And for hidden nodes, the little w's, wji is going to be equal, you're going to replace the old wji with itself plus the learning rate times the sensitivity of the hidden node j times the input I, which is the I should correspond there. We know what these sensitivities are. We calculated it before. And now we're going to apply it to our particular example. In our particular example, we know that we have one output, 2 hidden nodes, and 3 input nodes. So for our output nodes, we apply this formula for the indices k equal 1, because c is equal to 1, and j equal to 1 and 2 because we have 2 hidden nodes. And we know what this delta for the output sensitivity is. And for hidden nodes, for each one of these hidden nodes here, you're going to follow this. The number of input nodes is 1, 2, 3, so we're going to, the indexes are going to go 1, 2, 3, and j is going to go 1 and 2. Sorry, I forgot that this should have a 0 in it as well for the bias term. So that was my mistake. For these also should include the bias terms because the bias term is also multiplied by something. We know how to get the, the sensitivity in each case. So now I was promising you that we're going to look at a more general case. And this is a larger neural network. Of course, you could generalize it to many more. And as you can see, this is pretty messy. It has 3 inputs, 2 hidden layers, and 1 output layer. So in this particular case, each one of the inputs goes to each one of the first hidden layers, each one of the first hidden layers go to each one of the nodes of the second hidden layer, and each one of these plus the bias goes to the output layer. This is pretty messy and difficult to keep up with. Therefore, we're going to organize all of these weights into matrices. And all I did is gather all of the weights from all of the edges into these matrices here. And that I removed the edges just so that it wouldn't be so cluttered. But if you just look back at the previous slide and this slide, you're going to see that all of the weights are collected in each one of these matrices. Now, the output from the hidden layer, this is layer 2, or the first hidden layer, is going to be a vector of two scalars, the output from this and the output from that. So this is the super index 2 means we're talking about layer 2, and the subindex 1 means it's the first node of layer 2, and this is the second node of layer 2. This vector output is the sigmoid function applied to the weighted sums, these weighted sums over here. And these weighted sums are basically a vector of two weighted sums. We can write it like that, and we can actually show that if we called this matrix W1, then this weighted sum of layer 2 is going to be equal to W1 times the input vector. And the input vector, which includes the bias term, is simply the column vector 1, x1, x2, x3. When you pre-multiply the input vector times W1, you will get the net output, the weighted sum. Okay, and you're going to get a 2 by 1 vector. Once you apply the sigmoid function to the 2 by 1 vector, you get each one of these two outputs. Similarly, Y3 is going to have three outputs, one from here, one from here, one from here. And that's going to be the sigmoid function in each case from the weighted sum that each one receives. And the weighted sum is a vector of 3 because we have three weighted sums. And that weighted sum is going to be this matrix times this vector here. So this is forward propagation. And we now have the output of each one of these nodes from layer 3, this hidden layer, layer 3. All right, what about the output? The output has two scalars coming out, Z1 and Z2. And these two scalars are going to be the sigmoid function of the weighted sums. These two weighted sums are these two weighted sums right here. This is a vector. We can write it as a vector. And if we call this matrix W3, then that vector can be written as W3 times this vector Y3. Okay. So what do we have so far? In the forward propagation, we were able to obtain the vector of Y2, each one of these outputs, the vector of Y3, each one of these outputs, and the vector of the net output, the final output. And we also have the three matrices that transition you from each layer to the next layer. Now we need, in order to calculate the partial derivatives, in order to train our system, we need those deltas, those sensitivities. And we already calculated that the first sensitivity vector, in this case it's going to have two elements, is equal to the z vector minus the t vector. In other words, the t vector from the training set and the z vector, the output of our neural net. When I write the word diag, I mean a diagonal matrix where everything is 0 except the diagonal, and the diagonal has the elements of this vector. So this would be g prime of net out 1 and g prime of net out 2. And this is a 2 by 1 vector and a 2 by 1 vector. So when you pre-multiply it by this diagonal matrix, you're going to get a delta that is a 2 by 1 vector. All right. The next delta that we need, delta 3, is going to be delta 4, which we already calculated, times W3 transpose. And you can see that you can show that this product is exactly what we derived before, times this diagonal matrix of G primes. Now note that we don't use we don't calculate a sensitivity for the bias terms. Therefore, what you can do is discard the first row from this product. because we don't really need a delta for this bias term. The bias term is always going to be 1 no matter what, so there's no like sensitivity or error associated to it. It's just a plain old 1. So discard that one before you continue. Okay, and again, this is a diagonal matrix with all of the net terms of this vector along the diagonal. Okay? Delta 2 is going to be this matrix transpose times delta 3, which we just obtained. That gives us the delta 2 times the diagonal of this vector. Again, we don't use a sensitivity for the bias term. Therefore, you can discard the first row of this product here. You multiply that by the diagonal of net 1 and net 2. Those doesn't mean squared. It just means from layer 2. And now we have back propagated in order to calculate these 3 sensitivities. By the way, we never define nor do we use the sensitivity for an input layer, so you don't have to go all the way to delta 1. There's no need to do that. So now we have all the tools that we need in order to do our training. How do we do our training? Well, what are the things that we have? We have the delta 4, we have the delta 3, we have the delta 2. We have these outputs, and we know that when we want to update these weights, the way that we update them is we replace the old version plus the learning rate times delta 4, here it is, the term, the associated term, times the yj of that layer. Okay, so that would allow us to update each and every one of the terms of this matrix. If we want to update all the terms of this matrix, then we use this delta, this sensitivity for this hidden layer, and we use these y2s over here, and we use the learning. Again, we replace each term of this matrix with its old term plus the learning rate times the sensitivity times this term over here associated with the corresponding subindices. I told you the indices were an issue. We tried to keep them as simple as possible. Finally, we want to update the transition matrix between the input layer and the second layer, the hidden layer. And again, we apply the same steepest descent algorithm. We have the learning rate, we use this delta 2, and we use the corresponding input. By going through each one, you're going to be able to iterate and arrive to a good working weight for each one of these matrices, and that is the whole purpose of training the weighting, these weights for your neural net. So that's it. As I said, we're going to talk about regularization and other topics and random initiation for our next time. And thanks for joining us today.